Hello, Science 30s. Today I'm going to be talking about some of the light emissions and wavelengths and hopefully getting into telescopes. Hopefully we're keeping up on our notes and in our workbooks and we're working through some of the practice questions and understanding a lot of this vocabulary that we're coming across. I'm opening up with this image and kind of coming back to that EMR and this electromagnetic radiation emitted by the sun. Remember, the sun emits it all, but I like this image because you can see what is actually getting blocked, what is getting absorbed, what is getting hit by our atmosphere, and then what actually gets let through. And so what we see is the very, very short wave radios. So something in the length of 100 meters is getting blocked, getting knocked out. But then we're getting all the way to television wavelengths, and we're getting all the way to microwaves, and those come through. We do have some infrared coming in, and we get some blocked. And then we can see visible light makes it all the way through. And then back to blocking things out like UV. So we start to see that UVA, UVB, UVC, and that UVC, then X-rays and gamma rays are all getting blocked out. And then finally, we see on the very far end those solar wind particles, and they're coming through to make our northern lights. So I like this image. Take time to look through it on your textbook and kind of get an understanding of what gets let through our atmosphere and what actually hits our surface. Now, to continue on with a few more definitions and kind of key terms we want to talk about is our spectrum. And we're going to have a few ideas and effects that we see pop up. First one is this Doppler effect and explanation. If you go to the digital notes, you can click on the links or the videos that are attached to it, and it can lead you to other explanations. What we see here is what it is the sound effect and this Doppler effect based off of sound. So if you've ever heard ambulance or a fire truck, something that's coming towards you, you're going to hear it at one frequency and it's going to sound a little bit different. And then when it goes past you, it changes the pitch or it changes the frequency. And that's because it depends on the source that's making the sound and the observer. And if something is moving towards you, you can see those sound waves. If that car is moving towards you and you're standing on the right, if you have a person standing right here and the car is moving towards you, those sound waves are getting compressed and they're coming towards you closer and closer. And it's going to sound different. However, if you are on the other side and the car went past you already, or an ambulance and you're here, you can see that it's moving away and those wavelengths are getting further and further. So it depends where you're observing it and how the source is moving. For us, we call this a red shift or a blue shift, and we're mostly going to be talking about it because we're talking about stars and sunlight with this shift. And so when a sun is moving away, or sorry, when a star is moving away, not our sun, but a star is moving away from us, the observer on Earth, we see a slight red shift, and we have to account for that when we're trying to analyze the light coming off of it. Rather, if a star is moving towards us as the observer and it's emitting light, it's going to be slightly blue shifted for this spectrum of light coming in. So we're going to come across these words. We had refraction and hopefully remember them from last time with the definitions, but this is going to become important when we start looking into telescopes. And here we see a Galileo telescope where it has the different sizes of lenses because we wanted to start to look up to the sky and we wanted to start to see what these stars actually look. And when we look through a telescope and look at these stars, they all look actually different. We just see them through our naked eye as sparkling little dots, but if we could enhance it and see it on a very dark day, we're going to actually start bending these incoming light rays and we can start to study them. And so we're going to hopefully review refraction. And again, there is a link for you to click on when you actually click on the actual notes. Now we're talking about reflection and telescopes. So that last one was a Galileo telescope where it relied on refraction and bending the light. This one, we're relying on a curved mirror and reflecting it and bouncing it back, and then having our convex lens. So reflection is just bouncing off. So again, please click on the link in the detail notes and to learn more about these Newtonian telescopes and Galileo telescopes. So these telescopes, you just have to make sure you're understanding the root words, so refraction and reflection, and how they apply to telescopes. So remember, refractions, they use lenses and they use these large lenses, and they will break the light into that spectrum. Where reflection, they're going to use mirrors, and they can be made larger, but they do not break the light into colors. So two different styles of telescopes. Again, links in the D12 notes to practice with them. So it's great to have light microscopes. However, we now know during the EMR, there is other waves out there than just light. So now that technology has caught up with some of these ideas, we are able to actually have different styles of telescopes to capture different lengths of waves. And so the Hubble telescope in outer space actually can capture visible light, infrared, and UV. Other telescopes that we have on the ground can capture X-rays, radio waves, and even gamma rays. I like that third picture where you see a row of telescopes, and likely they are capturing very long waves of radios. And by stringing them all together, it's like you are making a very, very large telescope. So I mentioned the Hubble telescope in outer space, and it's a great telescope, but we have other outer space telescopes. This Chandra X-ray telescope. Why must we place some telescopes in space? We see how they have incoming X-rays. There's a mirror and an X-ray deflector to capture the images, but wouldn't it be easier to have this telescope on the surface? And that way we could fix it if necessary? Hmm. Well, of course we can't have the X-ray telescope in or on the ground because when we go back to this graphic, we see what actually gets blocked by our atmosphere is these X-rays. And we need to have an outer space telescope because it needs to be beyond our atmosphere so it can actually absorb X-ray emissions. Now, I talked about having different types of light being absorbed and being emitted, and how do we know how some things are composed of different things? This becomes an interesting question when we start looking at light. And so light and what it's being emitted by will have different properties, and it'll have different properties based off of what that substance is. So visible spectrum, all visible EMR. For us though, we have an emission spectrum. And so when hydrogen, let's say, gets excited and releases some amount of energy, it's going to release it at a very specific wavelength. Same thing if it is taking in white light and it's taking in this full bright white light, it's only going to absorb at a certain wavelength of light. And we're going to have this bright line and dark line emission set. And going back to hydrogen, we see this emission. So when hydrogen has a little bit more energy and the electrons are excited and they're in higher energy levels, but when they jump back down, they're going to emit a frequency of light at a very specific wavelength. Same thing if hydrogen is to get hit by light and have the electrons get excited with the energy, they're going to jump up a level and it's going to leave kind of a dark spot where it absorbs the light at that very specific wavelength. And this is where we see these two different spectrum lines where an emission is this where it brights up and it lights up this bright line, where an absorption is it's absorbing it and it's going to leave dark lines because it's absorbing at those certain light colors. So how do we measure this? Well, we have to use a spectroscope to actually break apart the light, and we see, based off of the source, what is that source made out of. So we take a light, let's say from the sun, and just use that as our source. It comes in, bounces off, we put it through a prism to break it apart, and then we can actually see, oh, perfect. What is being absorbed, what is being broken up, and we could see based off of what kind of energy is being absorbed or emitted, we can see what the stars are composed of. Each element will have its own unique pattern, and you can almost think of it as a bright line fingerprint. Neon has a pattern like this. Mercury will have a pattern like this. Hydrogen, one of the simplest one, is just these four lines, and we'll have kind of the hydrogen spectrum fingerprint like this. Here, helium, very close to hydrogen, has a spectrum pattern like this. And so when it has this emission pattern, you see it lights up ever so different than hydrogen. When we go through, there is practice questions on these spectra and the spectrum and dark and bright line emissions. So please make sure to go through the workbook, practice with some of these questions, and also I will include a link to help describe and how this was first discovered with some new technology on how do we actually measure these spectrums. Because, well, having just a continuous light source, it will emit this white light. Remember, we have to run it through a spectroscope and we have to break apart this light so we could actually see where these color lines are coming up. When we look at singular elements, it's easy to see, okay, hydrogen looks like this, neon looks like this. But now we can look at the spectrum of the sun, and you see that image below, and you can see all these bright lines and you can see the dark lines there, and you see the absorption pattern. So this is that dark line. So it's absorbing, and it's important to know, are you looking at an absorption or an emission? And here, these dark lines will act like a fingerprint, and it's kind of like a puzzle to say which elements will recreate this spectrum of the sun, and we can guess and take an educated guess about what that star or sun is made up of. Remember that when an element's excited and these electrons are jumping to higher energy levels and they absorb it, or when they drop down energy levels and they emit it, these two absorption emission patterns, they are going to be opposite to each other. So when we match them up together like this, the absorption, it's going to absorb the same light and same energy wavelength that it's going to emit. Just depends whether it absorbs it and leaves this dark line pattern, or it emits it and it leaves this bright line pattern. Looking at all these through these telescopes now, we can start to look at all this starlight, and the color of these stars are also going to correlate with the temperature of these stars. And that will be the next set of notes where we start to get into the pattern and start looking at different stars and what does the starlight tell us. And this is important when we came back to that Doppler effect of whether it's red shifted or blue shifted, it depends whether the star is moving away from us or moving closer to us because those emission and spectral lines are going to actually shift, which makes it even more difficult. So this is our star. This is the one we study the most. How do we know what it is made out of? So the sun, we want to know what's going on. And this is where we're going to start tying into astronomy and starting to look at different solar bodies and studying first with our sun, then other stars. Based off of the emission and absorption lines that we were talking about, we know our sun is really made up of a lot of hydrogen and that it is combining with helium. And when we have this reaction with two hydrogens coming together in this fusion reaction, we're making a helium and we are releasing huge amounts. Not even levels of nuclear energy, where nuclear energy is hundreds of times more energy than combustion reactions. This fusion is that next level. It is way more powerful and way more energy released than nuclear fission reactions. And this fusion is what occurs in the sun and different stars around in our galaxy. So lastly, remember, all forms of electromagnetic radiation are emitted by the sun and stars, and we're having all these little details on all these different wavelengths. So please make sure, work through your workbooks, look through the questions, answer and practice the questions in preparation for our quiz on Friday, April 3rd. Thanks. Have a great day.